Thank you very much. Good afternoon, good evening to everyone. When I was coming here today, I was thinking what can you explain to those people that remain at their room at 6:15 in the evening after dozens of speakers, and there's beer outside, do you know? There's free beer outside, right? So thank you for being here, even in this situation. Now, I would like to share with you, as the introductor has said, a very simple idea, which is try to discuss a little bit and to understand deeply which is the impact that the most advanced digital technologies are doing today to science in all scientific disciplines. So I'm the one that comes from the academic world today here, but also that affects a lot science, also has a lot of implications on industry, and there are many industrial sectors that today their competitive advantage depends on the use of these technologies. And something that is very important for science and very important for industry has to be very important for politics and for politicians and for geopolitics and for the US, China, Europe, etc. Things that Jorge Juan has been also mentioned before, right? And at the end, and last but not least, I would like to share with you our vision about why we think that our city is in a perfect position to take advantage of all these things in the near future. I have to say that I'm pretty optimistic about all these things in our city, but, well, of course, there's always grace there. I would like to open also the floor to your question if we have time about the impact of everything in our city, right? Let me just begin by introducing you to the frontier. The frontier is a machine, is a monster, is today the most powerful supercomputer in the world. It's been installed by HPE and AMD in the Oak Ridge laboratory in the United States. And our colleagues have been able to use this machine for reaching what we call the exascale, meaning we have for the first time ever in our planet a machine, a computer that works in the exascale, so performing more than 1 exaflop per second. Meaning something like that we have a machine able to perform 1 million of millions of millions of mathematical operations per second. Meaning 1 followed by 18 zeros of mathematical operations per second. Are you able to understand this? We don't. Nobody can really understand what does it really mean having a machine that is able to perform 1 million of things per second, right? But it works. It works very well, by the way. The first thing is, why do we need these monsters? Why do we need so amazing capacity of computing in our laboratories? Well, we need this because one of my first takeaways for you today is that the way in which we conduct science, we do research all over the world, is changing. We're in front of what we call the evolution of the revolution of the research paradigm. During the last even centuries, science in all disciplines, biology, physics, chemistry, engineering, medicine, it doesn't matter, have been doing a lot of progress following the scientific method. So you have your theoretical framework, you have your theories, your rules, your equations, you're in your office, you're working on it, and then you have natural experimentation. You have your laboratory, you have your wet lab, you have your microscope, your telescope, whatever. And in this dialogue, you push science to the frontier. You have your theory, you go to a laboratory to see if it's true or not. If there's something that does not work well, you come back to your theory, and with this dialogue, we can push science to the frontier. Now we've realized, 10, 20 years ago, maybe a bit more, that there are many fields in science that requires a little bit more. And it requires computing, data analysis, numerical simulation, artificial intelligence. It does not matter how we call it. It's almost the same for science. So we need theory, natural experimentation, and computing as the third pillar of the scientific activity today. And it does not matter if you talk about materials, medicine, climate change, geophysics, engineering, whatever. In almost all the scientific fields today, the top-notch science is being developed because of strong theoretical frameworks, amazing experimental laboratories, and the massive use of numerical computation to conduct research. This is a huge change for all the scientists all over the world, and it's been happening in the last 10 to 20 years. This is why we need this huge amount of computational capacities. But let me give you some examples to try to understand what's happening really there. I can talk about Gaia, for instance. Gaia is a satellite launched by the European Space Agency. It's going around the Earth, and it's trying to do something apparently very easy, which is making a map of our galaxy, right? Taking all the objects on our galaxy, on the Via Láctea, and trying to take all the information possible about these objects. The position, the velocity, the spectrography, the distance, everything. Well, the only problem is that in our galaxy there are about, well, it's not clear still, but more or less 100,000 million of objects. So it's a bit difficult to take all the information of these objects, right? Only in our solar systems, there are more than 150,000 objects that potentially can cross our orbit, which is something a bit worrying if you want to maintain life in this planet, right? This is a perfect example of how we can do top-notch research thanks to computing. There's no way without supercomputers of forecasting, of predicting, for instance, the orbit of these 150,000 objects in our solar systems. So astrophysics, astronomy, cosmology today is a matter of theory, large telescopes, experimentation, and of course computing. Let me give you another example. Today, we are fully able to simulate what's happening in a city in terms of meteorology, climate, weather, contaminants, pollutants, etc. This is, of course, because we know the equations of the climate. It's about chemistry, atmospheric chemistry, how it's embedded with the ocean, with the sea, etc. We know also how to use a lot of sensors in our city to measure experimentally many things. But we also are able today to simulate what's happening in a city thanks to supercomputers. So from astronomy, cosmology, astrophysics, to mobility, pollution, climate change, weather evolution, etc. Or even another example. These are real simulations of some compounds linked to a protein related to some disease. This is almost impossible to do in a lab, in a bench, in a wet lab, but it's already possible to do in a supercomputer. Only with this you cannot do almost anything, but using this technology together with your wet labs and together with your theoretical framework, you can do a lot of progress in science. I can finish these examples with another example, which is a bit frightening, I would say. The problem of protein folding, some of you come from biology, life sciences, etc., right? The problem of protein folding is something that has been worrying all the biologists all over the world for the last decades. The idea is trying to understand how a protein folds onto itself. This is very important because it depends on a lot of interactions between drugs and proteins, etc. But let's say that on the last 40 years, all the structural biologists in the world have been trying to develop statistical and computational methods to predict how it happens. And the most successful methods they have get, it's something about 40% of success. Only in 40% of the cases, these methods really give you a good result. Well, it's not much impressive, right? And then suddenly, DeepMind comes, they develop the AlphaFold algorithm, entirely based on deep learning algorithms, artificial intelligence, and after just 2-3 years of testing with new cases, 90% are successful. 90% of the cases, the algorithm is able to solve the problem. Well, this is an entire change of paradigm, because it's not only having a computer helping you to solve some problems that you're not able to solve analytically, and they solve numerically, that's fine, but I control what's happening there, which is a theoretical framework, the equations, etc., and the computer helped me to solve the problem. Fine, I can accept that. This is entirely different. This is I have a lot of data. I don't know how to build a theoretical framework there, but there's an algorithm that knows how to solve the problem. And what's more worrying, almost nobody understands how it works. I mean, artificial intelligence is something where you put information and get results. Let me just make it very simple. The explainability of what's happening inside, it's not trivial at all. In this case, what the people of DeepMind have done is just open to the whole worldwide community the algorithm. And everybody today is playing with this algorithm, trying to understand which are the rules this algorithm uses to solve the problem. So it's an entire change of paradigm. It's not only having computers helping us, it's having computing solving problems that we have been never be able to solve before. Okay, I've been talking about how high-performance computing, supercomputing, artificial intelligence, data analysis, etc., helps science to make progress. Let me just make a step forward. What about industry? Is that also impact to many industrial sectors, or is it just something for the scientific freaks that are able to work with these machines? Well, I can begin by talking about the typical large companies, Meta, Amazon, etc. Meta, for instance, is building what they call the world's fastest supercomputer. Well, it doesn't matter if it's the world's fastest or not, but it's true that these companies are beginning to use this type of machines for their plans, in this case for the metaverse or for whatever they are doing there, these people, right? But let me come just a bit down on more real or industrial problems. We can talk about combustion. We can talk about aviation, aerodynamics, digital twins for industries, simulation of new materials, simulation of the turbines in new engines, simulation of new aerodynamics of cars, everything regarding engineering, fluid mechanics, combustion, oil and gas, aerodynamics, aviation, automotive sectors. These all are sectors that are being fully disrupted by the use of these technologies. Let me say it in another way. Those companies that can have access to these technologies, and it's not only a matter of having the hardware there, it's a matter of having the people with the ability, with the capability of programming these machines to solve these problems, those companies will have a lot of competitive advantage in the future. We can talk also about, let me see if it works, yeah, other examples in life sciences, or Juan was talking now. This is a real example of a company called Metrology, probably most of you know them, using our human heart simulator to test new geometries and materials for cardiological stems. The alternative of doing this in a computer is doing this in real life. Of course, not with people, but with animals. And you can imagine easily all the problems with animal experimentation, which are still needed for many things, but it's very difficult to escalate, it's very expensive, there are ethical concerns, etc. If you're able to make it at the same level of precision in a supercomputer, you can escalate it and test for thousands and thousands of different proposals, which, by the way, give you the opportunity as a company to be near this dream of precision medicine. I mean, not developing something for everybody, but developing something fully adapted to the model you're using, and can be different depending on the age, the gender, the race, etc., etc., etc. So, this is pretty important for science. It has also an impact on industry. What about the politics? Let me just finish sharing with you what I think are the three main challenges for our future in these technologies, right? And I'm coming back to our city, to our reality. The first challenge we have is giving our scientists the access to the most possible powerful computers in the world in order to guarantee their capacity to compete with their colleagues in the States, in China, or in Japan. If you believe me, and you really believe that conducting research at the top notch at the world level needs this type of technologies, we need to give them access to the best possible machines in the world. This was began by Jean-Claude Juncker, the former European Commission President, in 2015, and I have to say that surprisingly, only 7 years later, we've achieved this goal. We have, right there in Finland, the most powerful machine in Europe, fully production since the last June. Last week, we inaugurated in Italy the second most powerful machine in Europe, top 3 and top 4 in the world, not bad at all, right? We're going to inaugurate in a few months the new Martorell 5 in our city, together with other small machines all over Europe. So with this new machine we will have installed in our facilities in just a few months, we've achieved, as Europeans, the first challenge we have for our near future in terms of science. We assure our scientists to have access to all the computational capacities they need to compete with their colleagues in other countries. It's not bad at all being able to achieve these goals as Europeans, and for me it's very important that one of these machines will be in our city, which reinforces our role in all these scenarios. So this is the first objective we had as Europeans, and of course, as always, these machines are very beautiful and are surrounded by a lot of high tech to maintain them inside a very good and nice building. You are fully invited to visit wherever you want. But I said we have, let's see if it works, 3 main challenges. The first one, giving access to our scientists to the best possible machines. Pretty achieved, done. Second objective as Europeans, much more difficult to achieve. Let's try to put inside these machines as much European technology as we can. If you can come to our facilities to see our beautiful machines, they work perfectly, they are amazing, a lot of petaflops available for other scientists in Europe, full of non-European technology, right? Full of non-European technology. This is, of course, not because we don't like European technology. This is because there's not European technology competitive today to serve this type of facilities. How difficult it is to achieve this goal? Well, let me just first answer another question. Why you're interested on putting European technology inside these machines? The software are going to go faster with a European chip that with the last chip from Intel or AMD or NVIDIA or IBM? Of course not. Why do we need our own technology? Well, there are many reasons. Let me just highlight 2 of them. First one, you can call it security, you can call it defense, you can call it whatever you want. Europe is the only country in the world which entirely relies on foreign technology on all our strategic facilities. And for strategic facilities, I'm meaning from things like this one to the data process centers of any administration, government, or whatever you want to call it. So first reason is security. Second reason is industrial competitiveness, especially because of the potential risks on future restrictions on access on certain technologies. Today, a car is almost a supercomputer with wheels. There's dozens of microelectronics components inside the car. Can you imagine what would happen to our automotive industry if tomorrow Joe Biden decides to multiply by 10 the taxes on exportation of American technology to Europe? Oh, this is not going to happen. We don't really know. It's not likely to happen, but we cannot trust only on what's likely and what's not likely for our future. So defense, security, industrial competitiveness, and last but not least, ethical concerns. We are really worried about our data. Jorge Juan was talking about the data in hospitals, etc. What our governments are going to do with our data and the algorithms that control us, that's fine. It's good to be concerned about these things. But you have to take into account that all this data, all your data, and all these algorithms are running on non-European technology. If you don't control the hardware, it's very difficult to control what's happening on top of the hardware, right? So we want to have more European technology inside our machines. Well, and there are happening things in our city, right, lately around this issue. Some American companies are beginning to come to our city announcing big investments. This is maybe too soon to be very optimistic, but I think we are looking at the beginning of something. Maybe we are for sure today one of the main hubs in research in computer architecture, supercomputing, AI, etc. in Europe, for sure. Maybe this will give us the opportunity of becoming one of the main hubs on the design of the future microelectronic devices, processors, accelerators, etc. So on research, we are very well. On infrastructures, we are on the top of the world. Maybe we have here a new opportunity coming for the next years. Okay, I've talked about 3 challenges. First one, giving access to our scientists, done. Second one, putting inside as much European technology as we can. We are just going there. Let me talk about the third challenge. The third challenge is feeding our scientists with even more and more and more computational power, because they need even more than the exaflops and the exascale I was talking before. Why they need so amazing amount of computational power? Let me give you an example. Natural language processing, computer vision, any artificial intelligence model like the AlphaFold I've talked before around the protein folding problem. You can see here, and sorry for putting here a lot of numbers, figures, etc. You can see here the amount of petaflops per day these models needs to be trained. And you probably, most of you have realized that this is a logarithmic axis. So every step is multiplying by 10, right? On the last 10 years, what we call the modern era of AI, the needs of computational capacity have been doubling every 3 to 4 months. Something that doubles every 3 to 4 months is not sustainable. We cannot give them the computational capacity they need if the need is growing following this path. So the third challenge is how we can build huge computers to give them the amount of computational power they need. So the question is, what's next? Are we able to give them this service, this computational power, following the Moore's law? Following this idea of putting every 18 months double transistors on the same surface? This is mainly what's the key issue in the last decades and the main reason why we've been able to growing and growing our computational capacity? No. We are already at 3 nanometers. Maybe we can go to 2 nanometers, maybe to 1 nanometer. There's a wall for the Moore's law. We need to figure out how we can feed our scientists with more computational power. Is the future neuromorphic chips? Is photonic chips? Is quantum computing? Honestly, we don't know. What we really know is they will need more capacity, and we are in a very good position in our city to conduct research as we are doing in many of these technologies, just in case one of them is the next breakthrough. And let me just, a final comment here about the quantum computing, because entirely honest, I'm a physicist by training, right? So I really love to talk about quantum. But I'm a bit tired of going to places where people are talking about quantum, like, you know, like next year, you would be able to go to the media market and to buy a quantum iPhone, right? No, this is not going to happen. So the quantum technologies, the quantum computing probably are going to disrupt some of the fields I've been talking about today. We are pretty sure of that. The technology is really promising. But let's be honest, we don't know when it's going to happen. Why? Because we are really far from having a real, commercial, productive machines. Now we are going to install 2 quantum computers in our facilities here in our city during the next 12 to 18 months. If you come to visit us, in 1 year and a half more or less, you will see 2 machines like this installed there. What does it mean? It means we are doing science, research. We are conducting experiments with these machines. This will be able to change the computing paradigm in the future. Maybe. There are very promising results all over the world, but are just promising results. We are still far from having these technologies as commercial ones, right? Just in order to summary, my 4 takeaways for you today. First, these digital technologies, HPC, supercomputing, artificial intelligence, data analysis, data numerical simulation, it doesn't matter how you call it because they're more or less the same. These technologies are having a huge impact of how we conduct research today. Second idea, it's not only a matter of scientists, it's not only a matter of science, it's a matter also of industry. Those companies in many sectors that will be able to use these technologies and that will have people able to understand these technologies will have a lot of competitive advantage against their competitors. Third idea, there's a very strong European strategy for autonomy there, and it's a huge opportunity for us. It's amazing how Europe has changed its view, wherever Europe is, in these terms. A few years before, discussing this was like a sin. Nobody were able to talk about if you have to prioritize our providers or not. Today, everybody in Brussels, and more than that, is fully aware of how necessity we have here, how neat is this, right? And last idea, we are in a very good position to play a key role around this, in computing, in AI, thanks to our talent, thanks to our facilities, thanks to our research, thanks also to our politicians, which I have to say they are not doing bad regarding all of this, right? So probably in a few years, we will see here in Barcelona happening many, many things about digital technologies and the applications to science and industry. And that's it for today. Thank you very much.